Okay. Hello, my name is Kirkby, and I'm a PhD student at the University of Birmingham in the UK. And I'll be talking to you about the WISCER CubeSat, which will be my project on the antenna development for the precursor, for the satellite as a precursor mission to low-frequency space radar research. So first, I'll just go over quick contents of my presentation. So I'll give an overview of the WISCER project and its scientific aims. I'll then look at the attitude disturbance modelling for the large antennas that are going to be on the satellite that I've completed, and then have a look at the in-progress antenna modelling, and then give a quick summary. So WISCER, the Wideband Ionospheric sound CubeSat experiment, will be, as I said, a precursor to the development of operational low-frequency synthetic aperture radar. Now, at the low UHF frequencies that this system will operate at, the ionosphere can heavily affect this system. And there are currently only limited measurements of this ionospheric effect appropriate for these systems. And so WISCER will aim to make these measurements by acting as a sounding satellite. So it would provide an emulation of a simple wideband signal that passes down through the ionosphere and is collected by a ground station on Earth where the data will be collected, thus minimising the data collection and transmission requirements on the CubeSat. For those who don't know, the ionosphere, which we aim to measure, is the upper atmosphere and is composed of ionised gas. It's the electrons in this ionised gas that react to passing radio waves and affect their propagation by scattering and other effects, and so affect the radar signal. The diagram on the right is a graph of electron densities in the ionosphere, showing the altitudes at which they occur. And all systems operating below 2 GHz are affected by passing through the ionosphere, but down at the approximately 400 MHz that WISCER will be investigating, it's even heavier, even stronger of an effect. So of particular interest for WISCER is the creation of small-scale structures in the post-sunset equatorial ionosphere, as these cause scintillation, scattering of trans-ionospheric signal, and have a large impact on the contrast of the radar image. As you can see in these two photos, the image on the left is a period when there's no scintillation, whereas the period on the right is a time when there's lots of scintillation occurring, and the contrast has been lost in the upper right of the image. So the requirements and limitations for the antenna on WISCER, which will be a 3U CubeSat. It needs to have 100 MHz bandwidth at around 475 MHz to emulate the SAR signal. It needs to be circularly polarized to prevent losses due to polarization rotation in the ionosphere itself. It needs to be directional to provide the gain we need, but also therefore smooth over any pointing errors that we can't get rid of. And there are currently 2 antenna options which we're developing side by side to ensure we provide the most suitable antenna. The first will be an inflatable conical helix antenna, which you can see deploying in the lower right. The helical arms of the antenna will be printed onto the exterior surface of an inflatable balloon. This type of antenna is circularly polarised and is directional without a ground plane if fed from the apex end of the satellite, which means we'll need to feed the signal from the pointy end of the balloon. And the aim is to, this balloon is to rigidise after deployment by a yet-to-be-decided method. However, one issue that you can see in this inflation video, which we hope to investigate, is that the connection between the satellite and the antenna is flexible and may cause problems for actual control. The second possible antenna is a cross-moxon antenna, which again you can see the active elements unit deploying in the bottom right. This active elements unit has the radiating arms that deploys from it, which phase at 90 degrees to each other to provide the circularly polarised radiation. And then a ground plane, which was hopefully a repurposed drag device that deploys with the antenna in order to make it directional. Now, the reason that both of these antennas need to be so large and deployable is that to get this smooth gain pattern, they need to be that size. So that even with the antenna pointing, we get reliable emission from the antenna, and so reliable scientific data on the ground. However, due to having large inflatable structures on large deployable structures on the balloon, attitude disturbances will increase, and so we wanted to investigate how strong these would be and what that means for the actual control system, and therefore the mass budget of the payload, scientific payload. And I have completed some work using the Princeton Satellite Systems spacecraft control toolbox to investigate this. We were looking at the question of, are the disturbances acting on WISCER large enough to rule out the use of 3-axis magnetic control as opposed to reaction wheels? And at this point we still have 3 candidate orbits that WISCER could go into, and so I needed to model the actual disturbances acting on WISCER at 750 kilometers for all 3 of these orbits. So if we look at some of the results for the best case example, for the cross-moxon in the sun-synchronous 750 kilometer orbit, the top graph is the actual disturbances acting on WISCER, which are dominated by solar pressure at this altitude, as you can see by the period of eclipse in the centre. And below that you can see the ACS dipole components that the onboard computer is determined is required to control the satellite against these. And as you can, the dipole on any component is limited to 0.2 ammeter squared as a technical limit. And as you can see, at some points it is reaching this limit and is having to be cut. And this is in the best case scenario. So here you can see the top graph is the torque being produced by that magnetic dipole. And you can see it roughly follows the disturbances correcting for them. However, there's big peaks where as a period of where we've lost control authority, but then we regain it, we're using the absolute maximum actual control torque that we can use to regain control of the spacecraft. And this is worrying. So you can see the angular deviation is given in radians on the lower graph. Is still small, about 10 degrees. However, if we you can see how quickly we lose the pointing, and if we'd have stayed in a period where we had the limited control authority, we would have lost the spacecraft or tumble at that point. So this is unacceptable, really, which shows that even in the best case, 3-axis magnetic control system cannot provide the torque requirements that we need, really, with the initial stage, the initial concepts for the antennas. And so we would have to at least use one reaction bit. So now moving on to the antenna modelling. So now we have a rough idea of the actual disturbances, and we know that these deployables are, whilst they may require a stronger actual control system than we would hope to use, they are feasible, and so we move on to the antenna modelling, see if we can change the antenna design, if we can shrink the size and still get this smoothness, then that will help the actual control system. So the first is the conical helix. The far field pattern, the far field radiation pattern you can see on the right shows that we have the required smoothness. We were looking at about 30 degrees, 30-degree beam width, and is, with the inclusion of the CubeSat body on the rear, is not affected. There are no sharp peaks or lobes or anything like that. And for this one, we've used the copper arms on the antennas that will be used in the first prototype that we've planned. The second the second is a cross moxon. Again, you can see the far field radiation pattern on the right hand side. Again, we've got the required smoothness, even with the ALDOS ground plane and the gaps within it. However, it was found that the ground plane had to be reduced in size from the standard off-the-shelf product, as for some reason we were getting asymmetries and lobes in the radiation pattern, probably caused by some kind of resonance with the structure because of its size. So that is actually good for the actual control system. Just quickly, these are graphs of the feed reflection coefficient, so a measure of how well the antenna is radiating. And the top one is the original design, and the lower one is an improved design to give the first had a not very wideband response. So we implemented some measures to try and improve this. And as you can see, with small modification to the radiating elements, we can get a much better wideband response from the antenna. I'll leave the summary and ask for any questions. I'll leave the summary on board and ask for any questions. Thank you.
Thank you very much. Any question from the audience? Please.
How do you control the inflation of the antenna in a vacuum?
So we plan to use cold gas generators. So only minimal pressure will be required, and so you can use these. You apply an electric current to a solid compound, and it releases gas that inflates the balloon.
I'm curious if you looked at the power requirements and common requirements for that payload yet?
Yes, we've done some initial budgets. The antenna will only need to be active for short periods whilst it's over the ground station. So for the rest of the orbit, it can collect energy and then transmit for short periods. So the power budgets look okay. We'll be using I think it showed in the slides, some deployable solar arrays to get there. Thank you.
We have another question.
So the frequency you chose is the assessment of the telecommunications frequency?
It's a foliage penetrating radar frequency.
Yeah, but you mentioned something about 475 megahertz, which I guess is the frequency you are using for ground for communication.
It is a communications frequency as well in it, but that'd be much narrower band,
Yeah.
so it should still be still.
But can you give an answer about the power?
Sorry, I can't quite hear.
Regarding the previous question, I want to ask the same question. Can you indicate the power in watts or milliwatts? The power.
What band of power? Sorry, I can't hear you. Sorry.
I mean the power of the transmitter.
How much is it? Can't remember off the top of my head. Do you remember, Matt?
We only need about half watt transmitted. It's very broadband, spread spectrum signal, so it'll be below the noise for most users on the ground.
Yeah, it's not trying to be a radar system. It's not providing an illumination, just a signal to measure.
Any other question for our speaker? Okay, thank you very much.
Thank you.
Our next